A rectangle with side lengths 1 and 3, a square with side length 1, and a rectangle R are inscribed inside a large square as shown. The sum of all possible values for the area of R can be written in the form m over n, where m and n are relatively prime positive integers. What is m plus n? What we can start here is looking at all the right triangles that are here, so we can break some of these triangles up to form right triangles. So break that up like that. And from here, noticing some similarity. So up here, if we call this alpha, since that's 90 degrees, this is 90 minus alpha. That's 90 degrees, so this has to be alpha. That's 90 degrees, so this is 90 minus alpha. This is also a right triangle, so this is alpha. Here, this is 90 minus alpha, because this is a right triangle. Since this is an isosceles triangle right here, two sides of one, these have to be the same angle measure, so that's alpha, and again, this is 90 minus alpha. Again, this will be 90 minus alpha, because this is a right angle, so this has to be alpha, because that's a right angle. And continuing here, that's 90 minus alpha, alpha, and so with this, all of these triangles are similar because they have the same angle measures. If we look at these triangles, we can call this angle beta. So that's a right angle. So this is 90 minus beta. Right angle, so this is beta. 90 minus beta. This is beta. And then this is 90 minus beta. So all of these are similar. And then this one in the middle is a bit of an odd case. We don't have similarity for this one in the middle. So from here we can start labeling sides. So noticing which triangles are congruent. So all of these similar triangles that I've dotted that have the hypotenuse of 1 are congruent. So we can label those sides. We can call the side across from alpha, just call that B, and the side across from 90 minus alpha, we can call that A. And so same thing here, so the side across 90 minus alpha is going to be A. This is also A. And the relationship, these are similar, this big one to these smaller ones, since this has a hypotenuse of 3 where these have a hypotenuse of 1. The sides on this triangle are going to be 3 times bigger. So this is across from alpha, so this has to be 3b. And down here across from 90 minus alpha, this would have to be 3a. And since this would be congruent to these because it has hypotenuse 1, this would be b. And we can set, since this is a square, this one added up has to be equal to this one added up. So if we add this up, b plus a, that should equal 3a plus b. And in solving this out, we get 3b is equal to a. And so from there, if we're solving for one of these right triangles, where the side length across from the hypotenuse is 1, we have the a and the b, but a is actually equal to 3b, so we can write the following equation. So 3b squared plus b squared is equal to 1 squared. And solving this through, we get b squared is equal to 1 over 10. So b is equal to 1 over root 10. Okay, so kind of make things easier to deal with. We can, if we scale everything up by root 10, and then as long as we just scale it back by root 10 at the end, we'll get to our answer. So what I mean by that is if we call b prime is just equal to b times root 10, which is 1. And so that means that a prime would be equal to 3, which means that the side lengths of the scaled up square are going to be 10 by 10. If you plug that in here, 3 times a prime is 9 plus 1 is 10. So the scaled up square is going to have side lengths of 10. So going back to this, now I want to look at side lengths of this triangle. So since we said that the side length across from 90 minus alpha, now I want to deal with the a prime and b prime. So this is going to be 3. And so let's have this the scale, what you multiply the 90 minus beta side to get the beta side, let's just call it w. So this will be 3w. And in terms of these sides, we'll be calling this a prime. So that would be 3, and that's b, so that's 1. So we have 3, 1, and 3w. So since this side has to be 10, this side will be 6 minus 3w. So now looking at this, that's 6 minus 3w. Again, since this is the side across from the angle beta, we'll have w times 6 minus 3w. And looking down here, we'll have, since this is 90 minus beta, we'll start down here. So 90 minus alpha, this is going to be 3. This is across from alpha. This is just, oh yeah, so since we'll talk about this side. So this has got to be, since this is across from 90 minus beta, and this triangle is congruent to this triangle because they have the same hypotenuse, the side across 90 minus beta, so this has to be 3. And since this would have to be then 3w because it's congruent to that triangle. And for this triangle, this isn't congruent to any of the other triangles here, but we know that in this type of triangle where you have this is similar to this, these side lengths are at a 1:3 ratio. So this side length would have to be w. So now we have the sides of this thing. What we can do now is add up. If we add up this side here, we know it has to be equal to 10. So we get 3 plus w plus 3 plus w times 6 minus 3w is equal to 10. And solving this through, we get 3w squared minus 7w plus. And that was after, you should end up with this. Just multiply by both sides by -1. And factor this, so 3w minus 4 times w minus 1 is equal to 0. So here we get this. So we get two values for w, and this kind of makes sense because this is asking the sum of all possible values for the area of R. And so since we got two different values of w, it looks like we're going to get two potential areas for R. So we can check both of these. So one is when if we have w equal to 1, looking up here, so w equal to 1, I want to try to figure out if we can figure out this side of R and this side of R. We'll call this side of R R1 and this side of R R2. So first for one of those sides, 3w. So since w is equal to 1, we get 3. So R1 squared is going to equal 3 squared plus 3 squared. So we get 18 is equal to R1 squared. So root 18 is equal to R1. Now looking at R2, plugging in w for those sides, 6, 1 times 6 minus 3 times 1, that's equal to 3, and 6 minus 3 times 1 is equal to 3. So same deal with 3 squared plus 3 squared is 18, so this R2 has to be root 18. But we want to scale back by root 10 to get the true area of R. And so to find the area of R, it's just going to be root 18 over root 10 times root 18 over root 10, and we get 18 over 10, which is 9/5. So that's one possible area for R. So now the other case when w is equal to 4/3, so finding those side lengths. So for the first one, finding for R1, so 3 times 4/3 is equal to 4. And the other side is 3, so it's going to be 4 squared plus 3 squared is equal to 1 squared. Doing this out, 25 equal to squared. So 5 is equal to R1. Now looking at R2 here, I have this. And then also we're going to have 6 minus 3 times 4/3, which gives us 2. So here we have 8/3. So here, so here, since we got 100 over 9 is equal to R sub 2 squared, it's going to be true that this is just equal to So we'll have 5. Yeah, R2 is just equal to, R2 is equal to square root of this, which is 10 over 3. And so now scaling back by root 10, for R, we're going to have 5 over root 10 times 10 over 3 root 10. That's 50 over 30, which is 5/3. Okay, so the sum of all possible values of R are, we got 9/5 plus 5/3, and adding those two together, it's 27/15 plus 25/15, which is 52 over 15. That's the sum of all possible values of R. And these are relatively prime, so this is M, that's N. And the problem's asking us for what's M plus N. That is 52 plus 15, which is 67, which is our answer. So the answer is choice E.